Linearization is essentially an approximation technique in which we are looking at a line, we're comparing the slope of that line, and using the slope of that line to predict a value that we may not know ordinarily. So oftentimes linearization is used with square roots, natural logs, functions that we can't just plug into and know what their values are. So like nobody should know the square root of 1.1. But linearization allows us to find that square root. So that's what we're going to do in this example here. We're going to find the linearization of the function f of x at x equals 0 and use it to approximate 1.02. So what we're doing is essentially looking at that function, and we are trying to predict a value that we can plug in to make it a value we do know. So we know the square root of 1. So if I make x 0, then I can use the square root of 1 in my problem. So we're going to say that f of x equals the square root of 1 plus x. We're going to make my a value 0 so that I get the square root of 1 plus 0, which is the square root of 1, which is 1. That means I also need f prime of a. So I need f prime of x. So that's 1/2, 1 plus x, negative 1/2 times the root of the inside, which is 1. And then I need f prime of 0. Which is 1/2. So then f of 0 and f prime of 0 in terms of the linearization function are f of a's and f prime of a. So then what I want to do is I want to approximate when x is 0.02. So what we're approximating in this case, because it's 1 plus x, we're approximating 0.02. So I think sometimes that's part of the problem too, is you don't know what you're approximating. We're not approximating 1.02. We're not approximating the square root of 1.02. We're approximating 0.02 because that's the x value you added to get that problem. So L of 0.02 is approximately f of a, which in this case is 1, plus f prime of a, which is 1/2, times x, which in this case is 0.02, minus a, which is 0. So then I get 1 plus 1/2 times 2 over 100. So then the 2's cancel, then you get 1 plus 100, which is 1.01. So the approximation of the square root of 1.02 is 1.01. Now, the last thing we talked about was, is that an overestimate or an underestimate? So what we have to do is think about the square root function and what that looks like. So the square root kind of looks like this, right? So then adding or subtracting inside that plus 1 is going to shift it to the left 1. So that's not going to change the direction it opens. It's not going to change its concavity. So now if you found a tangent line to that concave down function, is my tangent line points going to be above that or below that? And that's how you determine if it's an over or an underestimate. So since my points are always going to be above it, all of my predictions or linearizations are going to be overestimates. So if you actually look at the square root of 1.02, it's going to be slightly smaller than 1.01. So why understanding linearization is the ability to bring you one step closer to understanding how the calculator finds square roots. The closer and closer you get your approximation to the actual, the more accurate our approximation will be. This is much like a limit. So again, linearizations are kind of like limits. A limit isn't the actual value of that function, it is a predicted value. Same with linearization. It's not the actual, it's an approximation. So what we're going to move into next is differentials. So what are differentials? Differentials are a transformation of linearization where we're going to go back to Leibniz notation and we're going to talk about a function in terms of dy dx, and we're going to talk about respect with y, and instead of using like a's and x's, we're going to go back to dy's and dx's. So we're not going to do any more in here because then it's kind of like a review of differentials which we haven't talked about yet. We're going to go and talk about differentials now. But again, I think it was important to go back and look at that linearization to help us better understand sort of that technique. All right, so differentials, much like linearization techniques, are a way of approximating using a tangent line and a curve. The only thing new with differentials is going to be notation. The only thing new is going to be notation. So it says consider the function f and label a point on that graph C. So I drew the point in so all of our points are at the same spot. So that point I drew in is going to be the point C, f of C. And what I want you to do is draw in what you would consider to be the tangent line to that point. So remember, a tangent line is supposed to represent the slope of the line at the point you draw in. So what would the equation of the tangent line we drew in be? So essentially the equation of that tangent line would be the given function y minus, and again, just go back to the equation of tangent line, right? So it's y minus the point it goes through, which was my y1, which in this case is f of c, equals m, the slope of the red line, x minus c. And in this case, what does the m on the equation of tangent line in calculus? What is that? Well, that m is no longer slope anymore, but rather the derivative at that point. So instead of m, it's f prime of c. Changing my c value by moving it to the right, so we're going to go to the right, delta x. So now we're going to come up with this new point, delta x, to the right of c. So in terms of our function, that delta x point is really delta x plus c, because we move delta x units away from c. So c is the original point of the function, we move delta x units away from c. So if we're plugging in or talking about f, it's delta x plus c, which then means the point on the line is going to be at f of c plus delta x. Take all of that and now create your new tangent line. So now y is f of c. F of c is f of c plus delta x. My slope is going to stay at f of c because I don't know the slope of the line. My x is going to become f of c minus f of c. No f's in there. C minus x. The x values. So if you distribute that negative inside, you get negative delta x minus c. So what do we know about c minus c? Goes away. Now you have f prime of c times delta x. That f prime of c times delta x is what we are going to refer to in our future as delta y. So this right here technically would represent the change in y, right? That would represent the change from this point to that point. Agreed? So this is delta y. So f prime of c times delta x. Go back and think about what we said delta represented in old school. Delta y and delta x represent the change in y over the change in x. And what does f prime represent? The derivative. The derivative represents the slope. If you move delta x over to be on the other side, delta y and delta x represent change in y, change in x, or y2 minus y1 over x2 minus x1 equaling f prime of c, because you know delta y, delta x, change in rise, change in run. So essentially this is kind of where slope came from. Differentials, equations of tangent lines, and calc ultimately led us to slope. So the actual change in y, delta y, is forever now going to be given by f prime of c times dy, or delta x, where dx, sorry, not dy. I was looking at y. dx, where dx represents the change in the x value from one point to the other. That's what we're talking about today. Today is what we call differentials. Differentials are dx. They're dy. So delta y is the same as dy. So delta x is dx, delta y is dy. Instead of having to draw the triangles, we're going to use the d because it stands for that derivative. So when delta x is really small, then we call it dx. When delta y is also really small, we call it dy. And this is where our derivative came from. So f prime of x equals dy over dx. Same as delta x, delta y. dy equals f prime x dx. So instead of saying find the linear approximation, it may also now say find the differential. So the only thing that's different from linear approximation to differential approximation is notation. The only thing that is different is the notation. So it's find the differential dy when dx is 0.01. dx being 0.01 represents x minus a. dx represents x minus a. dx represents x minus a. So instead of having to take like x minus a to get 0.01, they're telling you 0.01. So again, here's your x is 2. So we have y equals 5x x to the 5th minus 4x cubed. So if this is y, I need dy. So we're going to find the derivative of y. What do we find the derivative of y with respect to x? So this is like finding dy dx. Derivative of x to the 5th is 5x to the 4th minus 12x squared. If I'm finding dy, how do I get rid of dx? We're going to multiply both sides by it, right? And now we're just going to fill everything in. They told me x is 2 and dx is 0.01. So you have 5 times 16 minus 12 times 4. So 5 times 10 is 50. 5 times 6 is 30. So you get 80 minus 48. 0.01 is really the same as 1 over 100. So 80 minus 48 is 32. So we get 32 times 100, or 32 over 100, which is 0.32. I'm thinking that would be a non-calculator question. Now, what does that mean? What does 0.32 represent? So then it represents the change in the y values when x increases by 0.01. So when x equals 2 increases by 0.01 or to 2.01. So that's the x value we're actually looking at, because it's 2 plus 0.01. So when x increases from 2 to 2.01, the y values increase by 0.32. So x goes up by 0.01, y goes up by 0.32. Okay. Find the differential dy when dx equals negative 0.02, given x equals pi and y equals sine of 3x. So we need to find dy So we start by finding derivative of sine 3x. So derivative of sine is cosine 3x times derivative of the inside, because it's a chain rule, derivative of 3x is 3. So we get cosine 3x times 3. Then we're going to isolate dy by multiplying both sides by dx. And then we're going to plug in x in dx. So I get 3 cosine 3 pi times negative 0.02. Cosine 3 pi is the same as the cosine of pi, which is the same as negative 1. So a negative times a negative becomes a positive, and 3 times 0.02 is the same as 3 times 6 with 2 decimals. So we get 0.06. So again, what that represents is the change in y with respect to the change in x. So dy is 0.06, dx is negative 0.02. So what that means is that as y increases by 0.06, x decreases by negative 0.02. Again, we're representing the differentials, which really represent the change in y and the change in x. So as x is decreasing by 0.02, y is increasing by 0.06. So our slope is always negative. So the rate of change is negative. Find differential dy when dx is 0.05 and x is pi. Sorry, dx is 2. If x plus y equals x times y. So what makes this one a little bit more difficult is now you have to go back to implicit. And you have to remember your dy dx rules. So that's why I started with using them. So derivative of x is 1 dx dx. Derivative of y is 1 dy dx. And then you have a product rule, so it's first times derivative of the second plus second times derivative of the first, which again would be like 1 dx dx, which is really just 1. So you get y. So it's important to remember our dy dx's, and then going back to what we had to do before, you have to get all the dy dx's on one side and everything else on the other. So we're going to have dy dx minus x dy dx equals y minus 1. So then you get dy dx equals y minus 1 over 1 minus x. So I factored out the dy dx and then divided to the other side. And then you get dy dx multiplying both sides by dx equals y minus 1 over 1 minus x dx. The second problem is I know x and I know dx, but I don't know y. And now my dy has a y in that final answer. So we have to go back to the original and plug in 2. And solve for y. So we get 2 plus y equals 2y, so I subtract y to the other side, and we get 2y minus y, which is y, so we're left with 2. So when x is 2, y is 2. And again, you could check that, right? 2 plus 2 is 4, 2 times 2 is 4. Be you happy? So now go back to dy. And we have 2 minus 1 over 1 minus 2 times 1.5. So 2 minus 1 is 1. 1 minus 2 is negative 1. 1 over negative 1 is negative 1. So we get negative 0.0. So again, differentials estimate the change of one variable with respect to the change of the other. Differentials represent the change of one variable with respect to the other. Linearization predicts a value. So again, differentials help predict the change. Linearization predicts a value. So if you have the radius of a circle increasing from 10 meters to 10.1, so again, here's the radius of the first one. Here's the new radius out to 10.1. How much has the circle changed? So if we wanted to talk about the circle's area, if the radius changes from 10 to 10.1, how much does the area change? That means we need to talk about area of a circle. So area of a circle is pi r squared. So the area of the circle when the radius is 10 is pretty easy. It's 100 pi. If I want to compare or find the changing area with respect to the changing radius, I have dA equals 2 pi r dr. So that's the change in area with respect to the change of the radius. So do you see how instead of having to do like dA dr and multiplying it, now we're talking about the change in the area and the change in the radius, keeping them to their variable sides. So dA is now 2 pi. R originally is 10. How much is the radius changing by from 10 to 10.1? 0.1. So they didn't come outright and tell you dr this time. You needed to find dr, which is 0.1. So 2 times 10 is 20. 20 times 0.1 becomes 2. So then you get 2 pi. dA would have what units? What would the units be of dA? So we're talking about the change in area. So area is always squared. So this would be 2 pi m squared. Again, taking into account R was in meters. The change in R would also be in meters, so you would have meters times meters if you were trying to figure it out that way as well. Approximate or error would just be comparing our answer to the real answer. So you would take a calculator and then find pi 10.1 squared and then subtract 2 pi, or subtract 100 pi and compare that answer to 2 pi. Homework is going to be in the book. I have 19 to 33 odd put down. Let me see if I still agree. going to be slope.